So we did this a while ago, but what we're going to try to understand is how is it that when something is orbiting something else or just going in a circle for whatever reason, then we say it is accelerating. There's a few levels at which we can understand why we can say that it is accelerating. One, well, if it's moving if it's moving in a circle, then it's changing direction. If it's changing direction, the velocity is changing, because velocity is speed, but within a particular direction. So the direction matters, and if the direction is changing, then it's not the same velocity. The velocity is changing, and if the velocity is changing, then the acceleration, then it must be accelerating. So that's one level we can understand it. But I think it's more powerful to understand it at a higher level, which is using the formula to actually show that not only is it accelerating, but also that the acceleration is towards the center of the circle. So we know that acceleration is equal to the change in velocity over time. Now, this makes sense if you just think about it in terms of speed. If we've got the final speed, take away the initial speed divided by time, it's how quickly the speed has increased. But as I said, it's not just the speed, it's the velocity. So it's how much the velocity has increased. Well, if the size of the velocity has not changed, how would we go about working this out? Well, we work it out the way that we normally work out vector addition and vector subtraction. We have here a diagram of something orbiting in anti-clockwise. So this, I guess, could be, it looks like it's the Earth orbiting the Sun. Just to be clear, the blue arrows are the forces, so force due to gravity. Notice, by the way, that they are the same on the Sun as this, and the same force that the Earth acts on the Sun. Oh my God, let me start the sentence again. The same force that the Sun causes on the Earth is the same force as the Earth causes on the Sun. So the same size, which is not what you'd expect. Anyway, we're not really focusing on that. We're focusing more on the. So yes, exactly. So despite the fact that they do in fact have the same force, which is not what we'd expect. The reason why we don't think they have the same force is because the Sun barely moves, but the Earth moves quite a bit, and we kind of visualize that the Sun is causing this huge force on the Earth. So how come it seems silly to think that we might think, well, the Earth is also causing a force on the Sun, but only a very tiny one. But no, it's the same actually. It's exactly the same size. The reason why the Earth moves but not the Sun is because the Sun is much more massive than the Earth. And if we think about the relationship between force and acceleration and mass, we know that F is equal to ma, and so A would be equal to F over m. And so if we have a huge mass, the acceleration is going to be very, very small. The force is the same for both of them, but for the Sun, which has a huge mass, it has a very, very low acceleration, so the velocity barely changes at all. It just stays where it is. Okay, but back to this idea of acceleration in terms of how can we show that it's towards the center of this planet. Well, if we look at the first situation, I've labelled v as u, the velocity is u in red, and at the second situation, I've labelled the velocity as v. So the u is the initial velocity, v is the final velocity. And like we have written here, it's v minus u over t. So we could say, we could get rid of the t for the moment because t is a scalar. So why don't we say that at is equal to v minus u, and because t is a scalar, then that's not going to change the size of the vector, it's just going to change the length of the vector. So we're really mostly interested in, is v minus u, according to this, it really is towards the center of this Sun, but how can we show that's the case? If you remember, when we add vectors, so if I've got a vector like this, which I'm going to call A, and I've got another vector like this maybe, which I can call B. Then when I add vectors, I just stick them head to tail like that. And so the vector of A plus B would be this. So if I actually label that new vector as A plus B, that arrow is, well, it's A plus B. So let's give these all different colors. So I'll make that one pink, make that one. And this obviously would be useful in your maths exam. And I'll make the sum of the two of them green. So just to be clear then, it doesn't... yeah, so yeah, and just to be clear, when we add vectors, we can when we work with these vectors, we can move them around, put them wherever we would like. We just can't change the size of them or the direction of them, and otherwise that would change their meaning. And so whilst I can add them A followed by B, I could also add them B followed by A, because just like in regular numbers, A plus B is the same as B plus A. And just to prove that it is the same, yeah, as you can see, they still get the same. They're still equal to the same A plus B. So then we go A. What about if we want A minus B then? So in that case, we'd want to make B minus, and what you've learned about in basic vectors is that the opposite direction backwards is minus. So if I flip the arrow around, then we'd want to actually relabel this as negative B. Then A plus negative B is the same as A minus B. So that would be like that. So now the vector of A minus B would be like this. I just need to flip that arrow now. So we'll make that green as well, and that would be A minus B. So that's how you subtract vectors from another. You just work out that a backwards vector would be the negative version of it. So how does this relate to what we're doing here? Well, we have a V here. We're trying to do V minus U, aren't we? So we're going to subtract the vectors. So let's. Oh, looks like I might have. Oh, I see what I've done. Okay, so I'm going to use an arrow. I'm going to do it slightly differently to how I did it before. It looks like I did green as the V, so let's label that as V. And we will move that over to here. As I said, you can move it around, do whatever you like with it, as long as you don't rotate it or change the size. And we'll do the U over here. I'll label that U. And do you want to just shape, maybe let's move this so it's less fiddly. Do you want to show me that V minus U really is the direction that my diagram is showing? Do you want to see if you can do that now? Yeah, there you go, you see. So when you do the same trick as you did with V minus U as I did with A minus B, you end up showing, or in this case it's negative U plus V, but as I said earlier on, it's the same thing anyway. And the yellow arrow ends up being from the beginning to the end, and as you can see, it's the same direction. We've proven it's the same direction because we moved it up there. So one other thing that needs to be explained here is how come the yellow arrow is not here and here, but it's actually somewhere in between. Well, it's because that this change from one velocity to another is happening constantly, all the time. Every infinitesimally small amount of time, the velocity is constantly changing direction. And so what we've done is we've taken a point where they're reasonably far apart, so you can more easily show this with a diagram. But you could also zoom all the way in and say this is U and this is V, and it would do the same. The trick would still work. It'd just be harder to show. And so because they're reasonably far apart from each other, then you'd have to show the average place between the two of them, which would obviously be the halfway point. And going from the halfway point, placing that yellow arrow, you see that it's pointing directly towards the center of the circle. So that is a much more comprehensive explanation about why when something is moving in a circle at constant speed, it is in fact accelerating. And not only is it accelerating, but it's accelerating towards the center of the circle. It is totally true to say that the moon is constantly falling towards our planet, or we are constantly falling towards the sun, whilst at the same time not getting any closer to it. And in fact, with the moon is constantly falling towards the Earth, but it's actually getting further away from it because it's actually not moving at quite fast enough that it's very, very, very slowly spiraling away from the Earth. But at the same time, it's falling towards the Earth, which seems a contradictory statement. But once you understand what is meant by that, you'll see that it works totally fine. Anyway, that's orbits.